All right. So in this chapter, we are going to talk about the sun. Um, so the sun is very, very different from all the other things that we've seen in this chapter. So in this chapter, we've learned a lot of things. We've learned about the planets, we've learned about asteroids and comets. We've learned about the moons that planets have with all sorts of interesting properties. But the sun is very, very different from all of these. It's a completely different beast. So the sun is a star, and it's the only star in our solar system. Uh, what is a star? A star is a glowing ball of gas which is held together by gravity and powered by nuclear fusion at its center. So the most important thing about a star, the distinguishing characteristic of a star, is that it's powered by nuclear fusion. So at the core of a star, you have nuclear fusion going on. And what is nuclear fusion? Nuclear fusion is a way in which energy is produced through nuclear reactions, and it's a very powerful way in which energy is produced through nuclear reactions. Nuclear reactions are also used in our nuclear bombs, so you know how much energy nuclear bombs can release. Same kind of mechanism happens in the core of the stars and produces energy, but of course on a far more gigantic scale than anything that our nuclear bombs do. So a star is a glowing ball of gas which is held together by gravity, and at the core of it you have nuclear reactions. In fact, that is one thing that distinguishes something that's a star and not a star. When we were discussing Jupiter, we talked about how Jupiter is not a star because nuclear reactions never started at the core of Jupiter. If Jupiter were a little more massive, then nuclear reactions would have begun at the core of Jupiter and Jupiter would have turned into a star. But that never happened for Jupiter. So Jupiter never became a star. But the sun is a star, and it's the only star in our solar system. Okay, now I have made this point throughout this course that we often like to imagine that um, there's something special about us. So for a long time, as we've seen in chapter 2, for a long time we thought that the earth is the most special place in the whole universe, because the earth is at the center of the cosmos and everything, including the sun, orbits the earth. That was the geocentric model, which Copernicus and Galileo and Kepler proved is wrong, and helped us see the truth, which is that the Earth is just another planet that orbits the sun. The sun is the thing that's at the center. So then we like to imagine that maybe there's something special about the sun. Maybe the sun is the most special star there is out there. As it turns out, there is absolutely nothing special about the sun, nothing. So we have studied billions and billions of stars. Literally billions of stars have been studied in a lot of detail. In fact, the whole previous century, the entire focus on astronomy was on stars. People were really fascinated by stars. So stars were studied to death all of the previous century. And so we have studied many, many stars. And what we find is that the sun is a very average run-of-the-mill star. So you can pick any metric you want. Like you can pick mass. The sun is very massive, but it's not as massive as the most massive stars, nor is it the most um, low mass star. Like there are many stars which have less mass than the sun, and many, many stars which have a lot more mass than the sun. So sun is somewhere in the middle. You can take the size. The sun is large, but it's not it's not the largest star by any. I mean, there are many, many stars which are way larger than the sun, but there are also many stars which are smaller than the sun. So again, by that metric also, the sun would be somewhere in the middle. Brightness. The sun does look really bright to us, but that's only because it's really close to us. So we are very close to the sun, which is a star. So obviously it looks so incredibly bright to us. But if um, the sun were far away from us, as far away as most other stars are, it would look like a little dot in the sky. And I think I'd shown you this picture, this artist's impression of what the sun would look like if it were seen from Neptune or Pluto. It would look like this little dot in the sky. But going by brightness also, you see the same thing. The sun is not the dimmest star, nor is it the brightest star. There are many stars which are dimmer than the sun, and many stars that are many stars that are brighter than the sun. So brightness also, the sun would be somewhere in the middle. And also composition, like we know, we are going to talk about what the sun is made up of. We are going to find that there's nothing special about that. Like most stars have similar compositions. So the sun is a very typical, very average run-of-the-mill star compared to all the other stars there are out there. So there is absolutely nothing special about the sun. All right. But it's very fascinating, as we are going to see today. By itself, it's very fascinating. All right, so let's talk about the properties of the sun. The mass of the sun is absolutely humongous by our standards. Its mass is 2 times 10 to the power of 30 kgs. 10 to the power of 30 is a very large number. It would be 2 followed by 30 zeros. Is that many kgs is the mass of the sun. To put that in perspective, that's 332,000 times the mass of the Earth. To remind you, the mass of Jupiter was only 318 times the mass of the Earth. That was the mass of the Jupiter, and we were raving about how massive Jupiter is. It's 318 times as massive as the Earth, but the Sun is 332,000 times as massive as the Earth. Okay, the size of the sun, or the radius, and to remind you, radius means from the center to the outer edge, the distance. The radius of the sun is 700,000 kilometers. So I have 696,000 here, but it's approximately 700,000 kilometers. The density of the sun is fairly low. It's 1410 kgs per meter cubed, and that should remind you of the densities of the Jovian planets, the outer solar system, like Jupiter and Saturn and all. They have similar densities like that. And the sun is entirely gaseous. So you cannot stand on the surface of the sun because the sun doesn't have any solid surface. Only the 4 inner planets have solid surfaces. Everything else, none of the other stuff in the solar system has a solid surface. So the sun is entirely gaseous. So you cannot really stand on the sun. Okay. Now, the sun rotates on its axis, just like the Earth does. So the sun has rotation on its axis. And you can measure the rate at which the sun rotates by timing sunspots as they move across the surface of the sun. So sunspots are these splotches, these large dark areas on the surface of the sun, and you can watch them go across the face of the sun. And you can actually, and by timing them, you can figure out how much, how fast the sun rotates. And let me just see if I can show that to you really quick. Just one second. Okay, so this is a picture, actual picture of the sun taken a few years ago. I think it was 2016 or something like that, or maybe 2018. And you can see the sunspots on the sun. And this picture was taken on the 22nd of June. And you can see these splotches that you see on the face of the sun. These are the sunspots. So these dark splotches that you can see, they're the sunspots. Now watch these. So this is June 22nd, June 23rd. See how the sunspots have moved. June 24th, they've moved even more. June 25th, they've moved more. So you can see every day they're changing position a little bit. See, you can just, if you want, you can just follow one of these sunspots. Like let's go back to June 22nd, and you can keep your eye on the one that's over here. Just this group over here. The next day, this group has moved over here. The day after that, it's moved further. The day after that, it's moved even further. The day after that, it's even further. And now you can't even see it. So you can see how all these sunspots are moving across, and that tells you that the surface of the sun must be rotating. And this is one of the things that that Galileo had figured out when he was studying the sun. He noticed the sunspots on the face of the sun, and I mentioned in chapter 2 that that was one of the things that convinced him that the geocentric model is all nonsense. Because one of the things that the geocentric model said is that objects like the sun and the moon, which are far away from the earth, they are closer to God, and so they must be these perfect orbs of light. And when Galileo looked at the moon, he saw that the surface of the moon looked pretty pockmarked with lots of craters and mountains and valleys. And then when he looked at the sun, he saw all these sunspots, which looked like these big blemishes. So all of that completely contradicts what the church had been saying for 200 years. I mean, for 500 years or so. And but then, being Galileo, he also looked at the rate at which the sunspots were moving across the face of the sun. And from that, he was able to measure the rate at which the sun is rotating. So you can use the sunspots, but you can time the sunspots to and find out how fast the sun is rotating. But that is not a very reliable way of finding the rotation rate of the sun, simply because you don't always have sunspots. So sunspots are things that come and go. So you don't have the same sunspots. Right now, I believe there are not too many sunspots on the face of the sun. So sometimes you have many of them, other times you don't have that many of them. All right, so a better way uh, of measuring the rotation rate of the sun, which I didn't put here, is to use the Doppler effect. And we are not going to bother with how you can do that, but that provides a better way of measuring the rotation of the sun. Oh, that's probably what I meant with the other methods. So you can measure the rotation rate of the sun. The sun exhibits differential rotation. So I talked about differential rotation when we discussed Jupiter and Saturn. Differential rotation means that different parts of the object rotate at different rates. So for the sun, it seems that the um, fastest rotation happens at around the equatorial region of the sun. So the midsection of the sun rotates fastest, and the polar regions rotate slower. Obviously, as we discussed earlier, differential rotation cannot be possible if the object is rigid, like the Earth obviously cannot do differential rotation. The whole thing rotates at once because it's a solid, rigid object. But the sun is not a rigid object, so it can have differential rotation, and different parts of it might rotate at different rates. So the sun rotates faster at the equator and slower at the poles. So at the equator, it takes 25 days to do one full spin. And at the poles, it takes 36 days to do one full spin. So that is differential rotation. The surface temperature of the sun is 5,800 kelvins, which is very, very, very hot by our standards. It's way above the melting point of any known material. So it's extremely, extremely hot, 5,800 kelvins. And you might remember that we had actually calculated this number using Wien's law in chapter 3, when we, was it chapter 3? Yeah, chapter 3. When we remember that with Wien's law, you make a radiation curve, and from the peak of the radiation curve, you get this lambda max, and from which you plug into a formula, and that gives you the temperature of the object. So if you do that, and we had actually done this calculation in chapter 3, you can easily deduce that the temperature of the surface of the sun is 5,800 kelvins. All right, now here is a diagram which we're going to keep referring to throughout this chapter, which tells you the structure of the sun. So the innermost part of the sun is called the core, and the radius of the core is 200,000 kilometers. So while you're looking at this, please keep in mind the radius of the Earth. The radius of the Earth is 6,400 kilometers. That's the radius of the Earth. All right, so just keep that in mind, just for perspective. The radius of the core of the sun is 200,000 kilometers, right? The next layer is called the radiation zone. That is 300,000 kilometers. The width of that is 300,000 kilometers. After that, you've got another region called the convection zone, and the width of that is 280,000 200,000 kilometers. So you can see how immense the sun is, right? But after that, you have a very, very, very thin region. Obviously, this diagram is not to scale, and that is called, that region over here is called the photosphere. So the photosphere is only 500 kilometers. So 200,000, and then you just have 500 kilometers. So the photosphere is very, very, very thin. And then you have the chromosphere, which is 1500 kilometers. So that's also pretty thin. Then you have a transition zone, which is around 8,500 kilometers. And then you have this diffuse region, this very, very diffuse region that is called the corona. So this diffuse region is called the corona. And so this is the structure of the sun, right? All right. Now, what is special about the photosphere? Photo means light. So the photosphere is the part of the sun from which the light of the sun is emitted. So when you are looking at the sun, which you should never actually look at the sun with your bare eyes, you should always have some kind of, have good protection in looking at the sun, like the eclipse glasses that people put on in 2017 to look at the sun. But if you look at the sun, what you're seeing is the photosphere of the sun, because all the light that the sun emits comes from the photosphere, right? Okay. All right. Now, the luminosity of the sun is a quantity which tells you how much energy the sun puts out every second. The entire sun puts out every second. And the luminosity of the sun is stupendously high. It's 4 times 10 to the power of 26 watts. So that is the luminosity of the sun, 4 times 10 to the power of 26 watts. So that's an enormous, enormous, enormous amount of energy that the sun puts out every second, right? That energy is released in every direction. As you can see in the arrows over here, that energy is released in every direction. The Earth just intercepts a small, tiny part of that energy, right? Okay, so before we talk about that, let me just make one comment about how much energy this 4 times 10 to the power of 26 watts is. It's an enormous amount of energy. But to put that in perspective, every second, the sun produces energy equivalent to the detonation of 10 billion 1 megaton nuclear bombs. Now, the most powerful nuclear bomb that has ever been built by human beings is called Tsar Bomba. And it was built by the Russians during the Cold War era in the 70s and 80s. There was a competition between the Russians and the United States, the Soviets and the United States, and who can build a more powerful nuclear bomb. So the Russians would build one, and then the US would try to one up that and build a more powerful one, and the Russians would one up that, build an even more powerful bomb, and so on. So this competition went on for a while, and Russia and the Soviets ultimately won, I guess, because they built the most powerful bomb in existence, and that was 50 megatons. That was the strength of that bomb, 50 megatons. So that gives you an idea of how powerful the most powerful nuclear weapon on our planet is. It's about 50 megatons. The sun, every second, the sun produces energy which is equivalent to the detonation of 10 billion 1 megaton nuclear bombs. So that is the amount of energy that the sun puts out every second. And we don't receive all of that energy. We only receive a small part of it because the Earth only intercepts whatever is coming in the direction of the Earth. Obviously, we don't get the energy that goes off in other directions. So we only intercept a small part of that energy, right? Um, if all the energy that the sun puts out could somehow be focused onto the Earth, suppose all of that energy hit the Earth, like just imagine putting these huge mirrors or something surrounding the sun, and you somehow focus all that energy onto the Earth, what would happen? In 6 seconds, all of the oceans of the Earth would evaporate. The amount, if that much heat were all to be concentrated on the Earth, in 6 seconds, all the oceans would evaporate. And in 3 minutes, the Earth's crust would completely melt. So that gives you an idea of how enormous, the enormous rate at which the sun puts out energy. So yeah, so it's a good thing that we only intercept a small part of that energy, because we obviously cannot handle any more than that. All right, so how do we know whatever we know about the interior of the sun? Because the sun is 93, is 1 astronomical unit away from us. So that's 93 million miles away from us. So how do we know anything about the interior of the sun? Well, most of our knowledge comes from making measurements and using a technique, a very powerful tool called mathematical modeling, right? So now the basic physics of the sun is not too difficult. I mean, conceptually, it's not too difficult. The details are very, very complicated and very highly mathematical, but conceptually, the basic physics of the sun is not too difficult. There are essentially two forces at work in the sun. One is the force of gravity, which is trying to pull everything inwards, right? That's indicated by these blue arrows over here. So gravity is trying to pull everything inwards. What is stopping that from happening is the outward pressure of the nuclear reactions going on in the core of the sun. So when these nuclear reactions happen, uh, they are, as you know, in any explosion, like matter is just flung outwards. So these nuclear reactions going on in the core of the sun fling matter outwards, and that creates an outward pressure, which prevents gravity from squeezing everything inwards. So this balance between pressure of nuclear reactions and gravity um, is called hydrostatic equilibrium. Now, the sun is only in its current state because these two forces are balanced. Equilibrium means a state of balance between the forces, right? So the sun is the way it is only because pressure, the outward force of pressure and the inward force of gravity happen to completely balance out right now. Now, just to make sure you're understanding this, what would happen if the force of pressure were weaker than the force of gravity? What do you think would happen? This could be an exam question on the final. Anyone? No one? All right. So the pressure of the force due to the nuclear reactions is acting outwards, and the gravitational force is acting inwards, right? So gravity is pulling everything inwards, and nuclear reactions are exerting pressure outwards. So my question was that what if the force exerted by the nuclear reactions is less than the force exerted by gravity, and that would just make everything contract, right? Because gravity would have its way, get its way in that case, and it would succeed in making everything contract, and the sun would shrink in size. On the other hand, if the force exerted by nuclear reactions is greater than the force of gravity, then the sun would expand, right? All right. Now, this is the basic physics of the sun, the fact that these two forces, pressure and gravity, are perfectly balanced. Now, the fact that these two forces are in balance implies that the temperature at the core of the sun must be extremely high. So, and that is because in order to balance all this gravity, you need enormously high pressure. And so enormously high pressure would require very large temperature, a large rate at which nuclear reactions are happening at the core. So it would require a very large temperature at the core of the sun. Okay. So this is one indication that the core of the sun must be extremely hot. All right. Now, in 1960, scientists were studying Doppler shifts of the solar spectral lines, which means that they were studying the light from the sun spectroscopically. And they noticed that the light that's coming from the sun would either be red shifted or blue shifted, depending on which part of the sun it's coming from. So for example, this part of the sun right here, the light might be red shifted, whereas this part of the sun over here, the light might be blue shifted. From this part of the sun, the light might be again blue shifted. This part of the sun light might be redshifted. So what does that tell us? So we know that when an object is moving towards us, the light from that object would be blue shifted. And if an object is moving away from us, then the light from that object would be red shifted. So that seems that different parts of the sun are moving towards us, away from us, towards us, away from us. And that indicates that the surface of the sun is probably rippling. So there are all these ripples going along the surface of the sun. So where do these ripples come from? These are internal pressure waves created by, these are actually waves that are traveling through the sun and show up on the surface of the sun. But these waves have traveled through the sun, right? So by studying the property of these waves, it is possible for us to understand, get some information about what's going on inside the sun. This is very similar in principle to when we talked about seismology in chapter 7. So in seismology, what happens is that you have an earthquake, and that causes these S waves and P waves to travel through the interior of the earth. And then by picking up these S waves and P waves all over the earth at various seismic stations, it is possible, and by studying, using that data, we can learn what's happening in the interior of the earth, because these waves have traveled through the interior of the earth. So that is called seismology. We are doing something very similar over here. We are studying the waves at the surface of the sun that have traveled throughout the interior of the sun. And so by studying these waves, we can get some information about what's going on in the interior of the sun. So this process is called helioseismology. So NASA has a spacecraft called SOHO, which is an amazing spacecraft. It's been in operation since 1995, and it is located at the L1 Lagrange point of the Earth. We learned what the L1 Lagrange point is in chapter 14. It is that one point between the Earth and the Sun where you can place, if you place an object over there, it will just completely be stuck at that point, and it would orbit the sun in synchrony with the Earth. So the L1 Lagrange point is located 1.5 million kilometers between the Earth and the sun. And so the SOHO spacecraft has been placed over there. And so it's constantly taking pictures of the sun and sending them to us. So it's a great way to study the sun. So there is this SOHO satellite, SOHO spacecraft, which is constantly studying the sun and collecting data. And then there's also this Global Oscillations Network group, which is a collaboration across many countries, which have these powerful telescopes pointed towards the sun at all times. And they're always collecting data regarding these ripples on the surface of the sun. Um, and they're always collecting it. So these spacecraft are located, these telescopes are located all over the world, so that as the Earth turns, there's always one or two telescopes always pointed towards the sun. So you have these telescopes in America, you have them in Europe, you have them in Australia, and so on. So as the Earth is turning, there's always some telescope that's pointed towards the sun and collecting data. So an enormous amount of data on the sun has been collected by SOHO and also this Global Oscillations Network group. And this data concerns the temperature, rotation, density, etc. of the sun. And what scientists do is that they feed this data into the solar model, and that allows us to enrich the solar model further, and then using that solar model, we can learn more about the interior of the sun. So the solar model is a set of mathematical equations, and you can fine tune those equations by giving it data. And then once you fine tuned those equations, then you can learn more information that you didn't know using those equations, right? And when you do that, you can verify whether the information that you're learning, that the model is telling you, is correct by checking it against more data. And if you find that it matches, then you know that the model is doing a good job. So that is how we have learned a lot about the sun. So we have built a solar model, and we have fine-tuned that model with an enormous amount of data that we've collected. And then using that model, we are able to learn more about the interior of the sun. So that is how we know so much about the interior of the sun. All right. And just since we are talking about SOHO here, let me just quickly show you the website for this spacecraft. Um, So this is the Soho website, and Soho is always watching the sun all the time because it's always pointed towards the sun, and so it's photographing the sun over all the time and sending us those photographs. So if you go to Soho, you can see almost um, live pictures of the sun at any time. So for example, um, I thought there was this. Okay, maybe the images. There was this, yeah, so this is, yeah, they had this thing on, maybe they've made a change to their website. They had these live shots of the sun. Um, oh, here it is, the sun now. Okay, so these are latest images from the sun. If you just look at this one, for instance, this is taken in visible light, and it's taken at, is the date over here somewhere? Yeah, I can't read it very well. Yeah, but it must be taken some a little earlier today. So these are pictures which are constantly being taken of the sun. It's just amazing that to think that we have technology like this, that we have a spacecraft which is 1.5 million kilometers away from the Earth, uh, constantly watching the sun, taking pictures of the sun, sending us those pictures, and we are seeing those pictures in front of us. So this is the view of the sun from the SOHO spacecraft, 1.5 million kilometers away from us. And in fact, you can also see that we don't have that many sunspots right now. So there's only this small group of sunspots. So we don't have that many sunspots at the moment. Okay, all right. Now, what do we know about the inside of the sun? So the density of the sun varies from uh, so the density of the sun at the core is extremely high, 150,000 kgs per meter cubed at the core of the sun. So the density is insanely high. To give you a comparison, the density of water we know is 1,000 kgs per meter cubed, but the density of the sun at its core is 150,000 kgs per meter cubed. Whereas at the photosphere, which is the outer layer of the sun, where one of the outer layers of the sun where the visible light comes out, the density is extremely low. It's only 2 times 10 to the negative 4 kgs per meter cubed. And in the corona, this it's so dense, so diffuse that it's almost a vacuum in the corona. So the sun's density is highest at its core, and then it decreases, and it's almost zero in the corona, right? Also, the temperature of the sun shows a similar profile. So at the um, surface of the sun, um, the temperature we know is 5,800 kelvins. That won't show on the scale of this graph because the scale of this graph is millions of kelvins. But uh, as you go into the core of the sun, the temperature rises to about 15 million kelvins. So that's the temperature at the core of the sun, 15 million kelvins. So the core of the sun is way hotter than the um, surface of the sun, which is only 5,800 kelvins. And we were talking about how hot that is, but the core is 15 million kelvins. And so it's way hotter. All right. Now, the next thing that we're going to talk about is how is the energy that's produced in the core through nuclear reactions, how is that energy transferred to the surface of the sun? All right. So near the core, the temperature is extremely, extremely hot, and the gas is almost completely ionized, and it's in a plasma state. So plasma means that the gas is so hot that all the electrons have been ripped off from their parent atoms. So remember that atoms look like this. So an atom consists of a proton. The hydrogen atom, the simplest one, consists of a proton and one electron. That's a hydrogen atom, neutral hydrogen atom. A helium atom consists of two protons and two electrons. That's a neutral helium atom. So these are the two types of atoms that you see inside the sun mainly. It's hydrogen and helium. But in the core of the sun, the temperature is so incredibly high that the electrons can't remain stuck to the atom. Like they are just kicked out. So just kicking out this electron and kicking out this electron. And so what you're left with is just a bare helium nucleus, which is a helium ion, right? So you have, so in the core you only have these ions. Everything is, you don't have any full atoms because electrons have been ripped out from all of the atoms. Even for the hydrogen atom, uh, normally a hydrogen atom would be one proton and one electron, but in the core of the sun, the electron just comes loose because things are moving so rapidly, the atoms are moving so rapidly and slamming into each other all the time. The electrons just cannot stay stuck to the atoms, so they are just knocked loose. And so in the core of the sun, you just have plenty of um, protons and electrons and ions. So that is what the core of the sun is. It's everything is ionized, and when a gas is in that state, we say that it is in the form of a plasma. So in the core of the sun, everything is ionized and you have a plasma. So energy is produced in the form of photons, these highly energetic photons, gamma ray photons. That is the form in which energy is produced, and by nuclear reactions in the core, and it travels outwards towards the surface as radiation, but very slowly. So let me just explain why the energy from the sun, the energy that's produced in the core of the sun, travels outward so slowly. So here is the sun, and here is the core of the sun, right? Okay, or let me just draw the core of the sun. It's probably better. So here is the core of the sun, and I just told you that in the core of the sun, you have just ions and electrons. You don't have any fully formed atoms, right? So you have ions. So hydrogen ion would just consist of one proton, and a helium ion consists of two protons. So everything is ionized, and ions have charge, right? And then you have these electrons, which have negative charge. So these have positive charge, and the electrons have negative charge. So energy is released in the form of these photons. We talked about what photons were in chapter 4. So I'm going to draw the photons as these blue circles. So these blue circles are the photons, and they're trying to get out of the sun. So they've been produced in the nuclear reactions, and they're trying to get out of the sun. They travel at a speed of the speed of light. The speed of light is 3 times 10 to the power of 8 meters per second. So let's assume that a photon can travel un, unimpeded out of the sun. So a photon starts somewhere at the center of the sun. We just want to find out how much time is it going to take to get out of the sun, right? The radius of the sun is, so let's just do that separately. So here is the sun. So this is the entire sun. The previous thing was the core of the sun. And this is the entire sun. So we are saying that a photon starts from the center over here, and it travels at the speed of light, and we want to find out how much time is it going to take to get out of the sun. So the radius of the sun is 700,000 kilometers. So I'll put 3 more zeros to make it into meters. So that's the radius of the sun. And so the question is, how much time will the photon traveling at the speed of light, how much time will the photon take to cover this distance. So this I can write as 7 times 1, 2, 3, 4, 5, 6, 7, 8. 7 times 10 to the power of 8 meters is the radius of the sun. And the speed of light is 3 times 10 to the power of 8 meters per second. So we learned in chapter 1 that time is equal to distance divided by speed. So the distance, I'm plugging in the radius of the sun, which is 7 times 10 to the power of 8 meters. And speed is 3 times 10 to the power of 8 meters per second. If you can calculate this, it comes to 7 divided by 3 is approximately, so let's see, 7 divided by 3 is 2.3. So approximately 2.3 seconds is the time it should take light that's produced at the core of the sun to just fly out of the sun, just get out of the sun, if it could travel unhindered. However, the photons that are produced in the core of the sun are not able to travel unhindered out of the sun. Why is that? Because photons are electromagnetic waves, right? So they happen to be affected by electrons and protons or anything that has charge. So a photon that's traveling in this direction, let's say it smacks into this proton right here, it will be affected by that proton. So the photon will bounce back and go this way. And then it smacks into this proton, and it might just travel this way, smack into this electron, and then it might be kicked this way and smack into this proton. And so you can see that it's having a really hard time getting out because it constantly gets kicked around by all these charged particles around it. And that's because the gas is in plasma form. If the gas were made of neutral material, like if it was just made of normal atoms, those are all neutral. So they would not have affected the photon at all, but photons are affected by charged particles. And so as a result of that, a single photon would follow a very, very zigzag path on its way out of the sun. So instead of traveling in a straight line out of the sun, the photon would follow a very, very, very zigzag path because it's constantly bumping into um, the, the ions and the electrons inside the core. So as a result of following a very zigzag path out of the sun, calculations show that an individual photon that's produced at the core of the sun would take something like 100,000 to 1 million years to get out of the sun. So just think about that for a moment. The light from the sun that you're receiving now, those photons that if you stand in the sun, the photons that are hitting your body right now, those photons only took 8 minutes to cover the distance between the Earth and the sun, the 93 million miles between the Earth and the sun. But prior to that, they were stuck in the sun between 100,000 to 1 million years after being produced. And so it's just crazy. So they were stuck in the sun for 100,000 to a million years. And then they only took 8 minutes to once they got out of the sun, they only took 8 minutes to cover the distance from the sun to the Earth. And now they're hitting your body or lighting up the ground outside your window. So, so this is a really fascinating thing. Um, so the photon energy that's released in the form of photons travels towards the surface of the sun as radiation, but slowly. So this "but slowly" is quite a loaded phrase here. So what I meant to convey is that it takes a really long time for the photons to get out of the sun. All right, so the photons make their very winding zigzag way to the end of the radiation zone. So photons are produced in the core, and then they follow this very, very zigzagged path. And then they get to the end of the radiation zone. At the end of the radiation zone, the temperature is a lot lower. and so it's not no longer a plasma over there. So when the temperature is lower, then you can have full atoms. So when the temperature is lower, you can have a neutral hydrogen atom with one proton and one electron, because the temperature is not that high. Only when the temperature is really high, the electron is knocked loose, right? So at the end of the radiation zone, it's quite far away from the core, so the temperature is lower, and you have fully formed atoms over there. And so the photons at that point just start getting absorbed by the atoms. So if you have a neutral atom like this, a photon might just uh, what I'm trying to do here is just send it to the next energy level. So this electron might just absorb that photon and jump up to a higher energy level, which is what I wanted to show here. So that's what starts happening. So the photons start running into these neutral atoms, and then they start getting absorbed by the neutral atoms. The neutral atoms will just absorb the photon and then jump up to higher energy states. And so when they do that, um, the photons start getting absorbed by the gas at the end of the radiation zone. And so the gas at the end of the radiation zone starts getting really hot, because it's absorbing these very, very highly energetic photons which are coming from the core, right? So the gas at the end of the radiation zone, beginning of the convection zone, starts getting really hot. So then what happens is, so this is what I was saying. So you have the core in the middle, and then you have the radiation, which is the photons coming in from the core. And around the end of the radiation zone or in the convection zone, these photons start getting absorbed by the gas, and that makes the gas really hot, right? And so now this really hot gas, what happens when you really heat up a gas? So what happens then, as we've seen multiple times in this course, is that when you really heat up a gas, it starts a convection starts happening inside the gas. And we talked about that earlier. Like if you take a liquid, for instance, the same thing would happen to a gas. But if you take water in a pot and heat up and put one side of the pot on an oven and start heating up this one side of the pot, I'd actually shown you a demonstration where you would see that the water over here rises up, and cooler water from here starts coming in to take its position. And so this is a convection current, and we've seen convection currents throughout this course. So as the um, gas at the bottom of the convection zone, which is the part of the sun right after the radiation zone, as the gas at the bottom of the convection zone starts getting hot, it starts rising up, and it forms these convection currents. So the gas starts actually the the convection zone is supposed to be over here. I drew the arrow at the wrong place. Let me just fix that. Yeah, so the convection zone is over here. So the radiation gets to the bottom of the convection zone and starts heating up the gas in the convection zone, and that creates convection currents. In fact, that's why it's called the convection zone. So these are these convection cycles that are produced um, as a result of the gas being heated from below. So you have these convection cycles, and then on top of that, you have more convection cycles and more convection cycles, and so on. And so this entire convection zone, you have a lot of convection cycles going on, right? And then at the end of the convection zone, the gas becomes so thin that it cannot that you can't have any more convection, because if the gas is very, very thin, then convection just doesn't happen anymore. So convection more or less stops when you get to the end of the convection zone, which is somewhere over here. And this is called photosphere. This region is called the photosphere. So here you just have very hot but thin gas. So it's so thin that it cannot do convection anymore. So from that point on, the the energy of the photons is just radiated out as visible light and infrared. And so that is how the photosphere puts out the light into the outside the sun. So that is how the energy is radiated from the sun. So you have the photosphere. Yeah. So we talked about how you have convection, which is energy transport through the physical motion of the gas. We talked about what convection is. Um, yeah, so the hot solar gas moves outwards while the cooler gas sinks inwards, creating a pattern of convection cells. So I showed you all these convection cells. And the deepest tier of convection cells would be around 10,000 kilometers across. And the topmost tier of convection cells is about 1,000 kilometers across. So these little guys, these small convection cells at the topmost tier would be around 1,000 kilometers. And then the convection stops at the photosphere, as I just said, because the gas density over there is too small. And so the energy is just transmitted once again by radiation. But from that point on, the radiation can just transmit, can just travel unimpeded. All right. Now, how do we know all this? Like, how do we know that the um, convection layer, at the top of the convection layer, the convection cells are very small and they're 1,000 kilometers across? And that is because we can actually photograph them. So this is an extremely high resolution image of a small part, a very, very tiny part of the surface of the sun. And here you can see these alternate light and dark regions, right? So what's happening here is that the light regions, or each bright granule, measures around 1,000 kilometers across. And what's happening there is that you have hot gas rising up. So the place where you have hot gas rising up, that appears as a bright granule in this image. And places where the cooler gas is sinking down are the dark regions in this image. And so you can see here that here is a light region, here's another light region. So if you look at this image, this schematic image over here, it makes it clearer. So you have hot gas rising up over here, and so that creates this bright region. And you have cooler gas sinking down over here, and that creates this dark region, right? And then again, hot gas rising up over here, that creates this bright region, and so on. So you have these alternate bright and dark regions, because these are the tops of the convection cells, and we can actually measure them. And it appears that each of these are about 1,000 kilometers across. 1,000 kilometers is half the width of North America. So each of these little granules is 1,000 kilometers across. All right. Yeah, so the brighter regions show matter rising towards us, and the darker regions show the matter sinking back in. All right, so it's 7:06, so let's take a 10-minute break. So 7:16 is when we'll resume. All right, so let's get started. So next thing that we're going to talk about is the solar atmosphere. So we can learn a lot about the atmosphere of the sun by studying the absorption spectrum of the sun. So we've talked about absorption spectra in chapter 4, and you know that when you have a continuous spectrum and you pass the light from that continuous spectrum through a relatively cooler gas, then what happens is that uh, the elements and compounds in the gas might absorb some of the wavelengths from that continuous spectrum. And so when you project that continuous spectrum, when you analyze that continuous spectrum or project it on a screen, you will see a bunch of absorption lines on the continuous spectrum. We talked about this in a lot of detail in chapter 4. So when you study the spectrum of the sun, we see lots and lots of absorption lines in the spectrum of the sun. And in fact, we can see 67 elements in the spectrum of the sun. 67 elements that are found on Earth are there in the spectrum in the atmosphere of the sun. The most abundant element is hydrogen, followed by helium. And interestingly, I think I've talked about this before, helium was discovered for the first time in the sun. And so it was not known on the Earth. So when people studied the spectrum of the sun, they saw these strange lines in the spectrum, and they had no idea what it was. They thought that it's probably some element that only exists on the sun and does not exist on the earth. But later on, helium was discovered on the earth as well. And so it was discovered first in the sun and then on the earth. So we can the solar spectral lines provide a lot of information about the sun. Okay, so here is the diagram showing all the spectral lines of the sun. So it goes from 4 440 about 450 excuse me. It goes from, yeah, 440. Yeah, you're supposed to, yeah, sorry, you're supposed to read it this way. So it goes from 390 to 460, and then the next line is 460 to 540, and then 540 to 610, and then 610 to 690. So it's more or less covering the entire visible spectrum, which is around 400 to 700 nanometers. And you can see how many spectral lines there are. All these dark lines are the spectral lines. So these spectral lines um, indicate the presence of many elements. And so this diagram shows us a few of them, like these lines over here indicate iron. These are some hydrogen lines. These lines are calcium lines, and so on. So there are many experts who can just look at these lines and tell you immediately what elements there are. These two lines are the sodium lines. So there are plenty of elements that that you can see in the sun by just studying these spectral lines. All right. Now, the layer that's just above the photosphere is the chromosphere. So we had seen how you have the core, and then you have the radiation zone, and then you have the convection zone. At the top layer of the convection zone, you have this very thin region called the photosphere, which is only 500 kilometers. And there, the gas is so thin that you don't have convection anymore, but the energy is just released as radiation. And so that layer of the sun from which the energy is released as radiation is called the photosphere, right? So we've discussed up till the photosphere. The next thing that we are going to talk about is the layer just past the photosphere, which is the chromosphere. So the layer just above the photosphere, which is up to 1,000 kilometers high, is called the chromosphere. The chromosphere emits very little light of its own, and it cannot be observed visually. That's simply because it's completely dominated by the very bright photosphere which is underneath it. So the photosphere emits so much light that you cannot really see the chromosphere above it. Um, However, at the time of a solar eclipse, you can get a glimpse of the chromosphere because at the time of a solar eclipse, the disk of the moon might be able to block out the entire photosphere. And so you can see this region uh, of reddish light that we can see. This is an image from a solar eclipse. So this region, which is sort of giving off reddish light, is basically the light from the chromosphere. And so that's the only time that you can see the light from the chromosphere, because usually it's overwhelmed by the amount of light coming from the photosphere. Now, the reason the chromosphere is so dim is mainly because its density is really low. So the photosphere, the density of gas is higher in the photosphere, much higher in the photosphere than it is in the chromosphere, and that is why the chromosphere is so much dimmer. And also, the reason that the light in the photosphere is has this reddish coloration is because of the H alpha emission line of hydrogen. You might remember from chapter 4, we had talked about one of the spectral lines produced by hydrogen corresponds to a jump of an electron from n equals 3 to n equals 2. And so that particular jump produced a photon whose wavelength was something like 664 nanometers or something like that, which is red light. So that particular type of light produced by that particular transition is what causes this reddish light in the chromosphere. Okay. Now, another fact about the chromosphere is that it seems that there are often these small solar storms which expel these jets of matter into the chromosphere. So the photosphere, the region underneath the photosphere, there might be some kind of turbulence, and that might shoot a jet of matter into the chromosphere. So there's a picture of that over here. This was taken by a Japanese spacecraft, and you can see how these jets of matter are shooting from just underneath the photosphere into the chromosphere. So these jets of matter, hot matter, which are often thrown into the photosphere, are called spicules. Um, and they have the effect of really heating up the chromosphere, right? So they come from just underneath the photosphere, and it's basically hot gas shooting out, and so it warms up the chromosphere, heats up the chromosphere. All right. Now, the beyond the chromosphere, you have the very diffuse region called the corona. So the corona can also be seen during a solar eclipse. So here's another picture of the solar eclipse, and this is kind of the one that we saw in 2017. Um, so this diffuse region, this that you can see, is the corona, right? So in this particular case, the disk of the moon has covered up both the photosphere and the chromosphere, and so you can only see the corona, the light from the corona, because the photosphere and the chromosphere have been covered up. And so you can see the chromosphere over here, and I mean, you can see the corona over here. Now, one really fascinating thing that scientists noticed in the 1920s. So in the 1920s, people wanted to understand the sun. And so they wanted to understand what's going on in the corona of the sun, right? But it's very difficult to study the chromosphere and the corona because they are completely overwhelmed by the light that comes from the photosphere, which is much brighter than both of these. So the only way you could study the corona without getting overwhelmed by the light from the photosphere would be at the time of a solar eclipse. So at the time of a solar eclipse, you just get that 1 minute or maybe less than 1 minute when the only light that you're receiving is coming from the corona, and the photosphere and the chromosphere are blocked out. So scientists would have everything set up, and they would measure spectrally, use their spectrometers to analyze the light from the corona at the time of a solar eclipse. So during the 1920s, when an experiment like this was done, um, what the scientists discovered were these very strange spectral lines in the light that's coming from the chromosphere, from the corona, and they were very surprised, like, because they'd never seen these strange lines before in any element on the sun. So they had no idea what kind of element would cause these strange spectral lines in the light. And they thought that maybe they've discovered a new element that only resides in the corona of the sun. And so they even came up with a name for it. They called it coronium. But later on, it was realized that this is actually not a new element. This is actually iron with 13 electrons missing. So to give you an idea of what that is, uh, atomic number of iron. So the iron has an atomic number of 26. So a normal iron atom would look like this. Where's my simulation? So it has 26 protons. So let me see if it will allow me to put 26 on here. It won't let me do 26. Can I put some more? Yeah, it's not going to let me do 26. But that's how it is. And so let's just do neon. So neon has um, yeah, so it will only do 10. So this is not quite the iron atom, because the iron atom has 26 atoms, 26 protons in its nucleus, and 26 electrons in its outermost shell. Actually, 26 electrons. Let me just draw it separately over here. So the iron atom looks like this. So the nucleus of the atom has 26 protons. So these P's all stand for protons. And it also has 26 neutrons. So I'd have to write a lot of N's to indicate the neutrons. So it's a heavy, relatively heavy nucleus. And then it's got 26 electrons, right? So these electrons are in these various energy levels. So this is the ground state, this is the one after that, and this is the one after that, and so on. So you have these electrons in these various energy levels. And I won't be able to draw 26 of them. Now, normally, when you have an iron atom, you can ionize it by just removing one or two of these electrons. So that's how we are used to seeing iron on the Earth. So an ionized atom of iron would have one or two electrons missing. What scientists realized was that the strange spectral lines that they were seeing in the corona of the sun actually corresponds to an iron atom which has had 13 of its electrons ripped out. So 13 of its electrons ripped out would indicate that the iron atom is at an incredibly high temperature, because it's only when it's at a very, very high temperature that the atoms, the electrons start getting knocked out of the atoms, right? So the temperature in the corona, in other words, has to be insanely high if iron can only exist in this highly ionized state, right? So that was where these strange spectral lines were coming from. It is iron these are the spectral lines of iron in a very highly ionized state with 13 electrons missing. And so that tells us that the temperature in the corona is extremely high. So the very high ionization of iron implies an extremely high temperature in the corona. Um, so um, so it appears that we were talking about how the temperature keeps going down. The temperature of the sun is the highest in the core, right? That's where all the energy is being produced. The temperature is 15 million kelvins at the core. Then as you go outwards, the temperature keeps going down and down and down until you get to the photosphere, where the temperature is only 5,800 kelvins. And then it gets even cooler. In the chromosphere, the temperature is 4,500 kelvins. It's cooler. But then after the chromosphere, the temperature starts rising again. So there is this transition zone right after the chromosphere, where the temperature keeps on rising, as you can see in this graph. And it just rises and rises and rises and shoots up to almost 3 million kelvins in the corona. So the temperature in the corona of the sun is extremely hot. It's 3 million kelvins. It's much hotter than the temperature of the photosphere. So this is a thing that scientists still don't fully understand. Like, why is the temperature in the photosphere so much cooler, and then the temperature in the corona is so incredibly hot? Um, so this is called the coronal heating problem, which is still not fully understood. But the guess that most scientists have is that the reason that the corona is so hot is because of these spicules, which are these jets of hot matter, which have been found to often shoot out of the from the interior of the sun into the corona. And so maybe these dump a lot of energy into the corona, and that's what causes it to heat up. So that could be one reason, but it's not something that's fully understood. So this is called the coronal heating problem, and it's the question of why the temperature of the corona is so incredibly high in comparison to the temperature of the photosphere. All right. Okay, so we talked about the corona. All right, now it turns out that very fast moving particles, which are mostly protons and electrons, and alpha particles are helium nuclei. So, so coming back to this simulation over here, uh, So a hydrogen atom is made up of one proton and one electron. Sorry, one proton and uh, one electron. That's a hydrogen atom. And if you were to remove this electron, then you get a hydrogen ion, which is just a proton, right? A helium atom is made up of two protons and two neutrons. That's what a helium nucleus is made up of. And in order to make this neutral, you need two electrons. So that's what a helium nucleus is. But when you ionize this helium nucleus, that means you remove these two electrons. And so you're just left with the nucleus of the helium atom. The nucleus of the helium atom is sometimes called an alpha particle. And I talked about this in chapter 7 when we discussed radioactivity. So it turns out um, that a bunch of protons, electrons, and alpha particles, which are alpha particles just means these nuclei of helium atoms, which consists of two protons and two neutrons, they are constantly escaping from the sun at very high speeds. And this stream of particles, which are always coming out of the sun, is called the solar winds. So these particles travel at insanely high speeds. So 500 kilometers per second. So that's 1 million miles per hour is the speed at which these particles are traveling, 1 million miles per hour. And so they reach, that's still much slower than the speed of light, but still it's a very, very high speed. So they reach the Earth in just a few days. So it just takes them a few days to cover the 93 million miles um, to from between the sun and the earth. Um, so the reason that you have these very high speed particles coming out of the sun is the high temperature of the corona. So we talked about how insanely hot the corona is. And so the very high temperature of the corona um, causes the coronal gas to be so hot that these particles can just escape the sun's gravity and get out of the sun. So when the temperature is very hot, the particles are moving very fast, and so some of them might be moving faster than the escape speed of the sun, and so they're able to just get out of the sun's gravity and fly out of the sun. Okay. Um, the sun loses about 2 million tons of matter every second. So the sun is losing 2 million tons of matter every second in the form of these solar wind particles. But the sun is so incredibly massive that this has not even made a dent to the size of the sun, the mass of the sun, even though it's losing 2 million tons of matter every second. All right. Now, we've talked about sunspots before. So the sunspots are these dark spots on the face of the sun. Here you can see another image of some sunspots. Um, they were first studied in detail by Galileo, as I mentioned. The typical size of the sunspots is 10,000 kilometers. So that is about the size of the Earth. So the diameter of the Earth is 12,000 kilometers. So the typical size of a sunspot is about 10,000 kilometers. So the Earth would easily, 1.5 Earths would easily fit inside this sunspot right here. So that gives you an idea of how large the surface of the sun is. Um, so yeah. Now, typically the sunspots occur in groups, and they don't last. So they appear and disappear. I showed you the today's picture of the sun when we were talking about Soho today, and you saw that we hardly have any sunspots right now. So sometimes you have a lot of them, sometimes you don't have that many of them. And the reason that they are dark, the reason that they appear dark, is because their temperature is lower than the average temperature of the surface of the sun. So the average temperature of the surface of the sun is 5,800 kelvins, as you know. But the temperature of a sunspot is only about 4,500 kelvins. So the sunspots are very hot, but nowhere near as hot as the rest of the surface of the sun. And so since they're a little bit cooler than the rest of the surface of the sun, they appear to be darker. All right. Um, it turns out that each sunspot is surrounded by a cool, dark inner region called an umbra and a warmer outer region called a penumbra. And here is a amazing high-speed, high-resolution image a sunspot showing the granules surrounding it. So this is a high resolution image of a sunspot. All right, now let's talk a little bit about magnetism on the sun. So there is a phenomenon in physics called the Zeeman effect, which can provide detailed information about the magnetic field at any point on the solar surface. So you might wonder, how can we possibly know about the magnetic field on the sun? We are 93 million miles away from it. It's not like we can take a little magnet and hold it near the sun to see how strong the magnetic field is. But we have a very powerful tool called the Zeeman effect. And I'll just very, very briefly explain what that is. So suppose you're analyzing the light from a particular source, and you see what spectral lines it makes, right? Now, suppose that source, which is producing the light, has been subjected to a strong magnetic field. Then what's going to happen is that you will see an effect on that in the spectral lines. So that the spectral lines will either get broadened, or they'll get split into more lines, and so on. So by and so this phenomenon is called the Zeeman effect. So the Zeeman effect is the broadening or the splitting of spectral lines by a magnetic field. So when we study the spectral lines from the sun, if we see any evidence of the Zeeman effect on those lines, we can tell that. Uh, I mean, let me rephrase that. So when we study the spectral lines from the sun, all of them have the Zeeman effect going on, and so we can learn a lot about the magnetic field on the surface of the sun by studying the spectral lines, by studying the Zeeman effect in the spectral lines of the sun. So we find that the magnetic field in a sunspot is typically 1000 times greater than the magnetic field in neighboring regions. So the sunspots have extremely strong magnetic field. And so that suggests one reason why the sunspots are cooler than the rest of the sun. It's probably because the abnormally strong magnetic fields will tend to block or redirect the normal convective flow of gas. So earlier we studied how on the photosphere you have these regions of warm gas rising up, which produces bright spots, and then you've got cooler gas sinking down, which produces these dark spots. So it's possible that this normal convective flow is blocked or redirected by the very, very strong magnetic fields that exist in the sunspots. And so that's probably why they have this darker appearance. Um, okay, we can skip these other two bullet points. All right. Now, here is an amazing image of the magnetic field lines, yeah, on the surface of the sun, a small part of the surface of the sun. So there is a group of sunspots over here, and you can see another group of sunspots over here. I wish I could change the color of my marker. Let's see if I can do that. Okay, so you can see a group of sunspots over here and another group of sunspots over here, and you can see these magnetic field lines going from one sunspot to another. Now, magnetic field lines are invisible, so we can't really see them. The reason that we can photograph them in this image is because often these extremely fast moving particles will travel along the magnetic field lines. Um, and so these very, very fast moving particles uh, will often give off X-rays. And so as a result of that, or actually ultraviolet light, so these very fast moving particles will give off ultraviolet light. So if you take a picture in the ultraviolet, you can see the ultraviolet light from the very fast moving particles, which are following the magnetic field lines. And that is what we see in this image. And as a result of that, we see this amazing image of magnetic field lines between a pair of sunspot groups. Um, all right. Okay. Now, I told you that the sunspots don't are not constant, so they're there sometimes and then they're gone. It turns out that there is a sunspot cycle. So the number of sunspots reaches a maximum roughly every 11 years or so, and then falls off to almost zero. So the solar cycle uh, and that's called a solar cycle. So the number of sunspots reaches a maximum every 11 years or so, and then falls off to zero, and then again rises up. It takes another 11 years to go up to a maximum again, and so on. So that is a solar cycle. And so the solar cycle 25 started in December 2019. So right now we don't have, it's only to 2021. So the number of sunspots is gradually increasing now, and it will keep on increasing until we get to the next solar maximum. So we are close to a solar minimum right now, and that is why we don't um, have that many sunspots. And just to be clear, solar maximum means when we have the maximum number of sunspots in the sky, and solar minimum is when we have a minimum number of sunspots in the sky. And we are close to a minimum right now, so that's why we don't have that many sunspots right now. All right, any questions so far? I've been talking for a long time. I forgot to ask if anybody has questions.
I don't.
Okay, all right. Now, the active sun. So it turns out that the photosphere surrounding a pair of sunspots can be very violent. And sometimes it might spew large quantities of energetic particles into the corona. So the sites of these energetic events are called active regions. So the photosphere near the sunspots often seems to be quite energetic. So you have all sorts of explosions and blasts going on in the region of the photosphere that's close to some sunspots. Um, so those regions are called active regions, and there are three types of of these very energetic events that we usually see in these active regions. So the first one is called a prominence. So prominences are basically loops or sheets of glowing gas which are ejected from the active regions on the solar surface. So there are these huge loops of gas which come out of the surface of the sun, and then they go back into the other into another part of the surface. So here is one example of a prominence. So you can see this huge, gigantic loop of gas coming out, and then it again goes back into the sun. So the typical size of a prominence is 100,000 kilometers. So that is about 10 times the size of the Earth. And they're probably caused by magnetic instabilities in the strong magnetic fields around the sunspot groups. So these prominences can release enormous amounts of energy, like 10 to the power of 25 joules, and they mostly consist of fast moving particles and radiation um, that comes out. So here is another prominence in this picture right here. So prominences are these loops of glowing gas which come out of the sun and then go back into the surface of the sun. Now, flares are much more energetic events than prominences. So a solar flare, is an explosion on the sun's surface, um, which sweeps across the entire region in minutes and blasts matter into space. So an explosion, a solar flare is like a bomb, a gigantic bomb going off on the surface of the sun. So the heart of a solar flare can have a temperature of 100 million kelvins. So the temperature at the core of the sun, the temperature on the surface of the sun is only 5,800 kelvins. The temperature at the core of the sun is 15 million kelvins, but the temperature of a solar flare when it happens can be 100 million kelvins. So when a solar flare happens, it produces an intense emission of X-rays and ultraviolet radiation, and the particles which are produced in the flare are so energetic that the magnetic fields of the sun cannot hold them back, and so they just fly out into space. In the case of a prominence, the particles that come out of the sun in the explosion are not that are still very energetic, but still they're not energetic enough to escape the magnetic field, and so the magnetic field again guides them back into the sun. But in the case of a flare, the particles are so energetic that the magnetic field is not strong enough to bring them back into the sun, so these particles will just fly off into space. They're just blasted into space. So that's a solar flare, and you can see an amazing image of a solar flare going off over here. All right, the third kind of event that happens in active regions is called a coronal mass ejection. So these are gigantic bubbles of ionized gas, or plasma, that separate from the solar atmosphere and escape. So a large bubble of ionized gas might just separate from from the atmosphere of the sun and just fly off. So that's called a coronal mass ejection. So these happen about once a week at during sunspot minimum, and they can happen 2 to 3 times a day during solar maximum. So you have a lot of these coronal mass ejections during solar maximum. So when a coronal mass ejection happens, so they fly off in random directions, but occasionally one of them might come pretty close to the Earth, and at that time, it might interfere with the Earth's magnetic field. So the Earth's magnetic field normally looks like this. We've seen this in chapter 7. You have the magnetic field lines coming out of the magnetic North Pole and going into the South Pole. And we have seen how so that's what the normal magnetic field looks like. And here is a coronal mass ejection coming towards the Earth's magnetic field. When it gets closer, what happens is that the magnetic field lines of the Earth get all wonky inside, because the coronal mass ejection also has magnetic fields. So combining with the magnetic fields of the Earth, the magnetic field of the Earth gets completely wonky in that region. And so temporarily, the Earth loses its protection from solar wind particles because the magnetic field is disrupted uh, when the coronal mass ejection is passing through it. So during this time, if you have solar wind particles coming in, the sun is always giving off solar wind particles, so that's relentless. So the solar wind particles that come in have no problem um, passing through the Earth's magnetic field, because the Earth's magnetic field is all wonky now, um, with the coronal mass ejection, and so the solar wind particles will now slam into the upper atmosphere of the Earth, right? And we know what happens when solar wind particles slam into the upper atmosphere of the Earth. We studied this in chapter 7. Uh, we know that they cause these amazing displays of light, which are called auroras. So typically, we only see the auroras in the north and the south pole of the Earth, but at the time of a coronal mass ejection, they might be seen anywhere. There was a coronal mass ejection which happened about 8 9 years ago, maybe in 2012, and auroras were visible from Alabama, because the magnetic field over Alabama, Earth's magnetic field over Alabama was disrupted, and as a result of that, auroras were visible in certain parts of Alabama. Uh, but these coronal mass ejections probably last for 1 day or two, and then they pass on, and then the Earth's magnetic field comes back to normal. However, since disrupting the Earth's magnetic field can have really terrible consequences for us, like it can uh, affect affect satellites in space. It can also affect power communications on the ground. um, there was a city in Canada whose entire power supply got cut off for a day when a coronal mass ejection like this happened. So they can be dangerous in principle, but usually most of them just pass by the Earth, and so they don't cause too much problem usually. All right. So unlike the photosphere, which mostly radiates visible light, the very hot corona radiates in X-rays. So the corona usually produces a lot of X-rays because its temperature is extremely hot. In chapter 4, we learned about how the kind of radiation produced by a material depends on the temperature of the material, right? So at our temperature, we are mostly giving off infrared radiation, but when something is very hot, it produces visible light. When it's even hotter, it produces ultraviolet. Uh, but the corona is so incredibly hot that it produces X-rays, right? So the very hot coronal gas radiates X-rays. That's actually a good thing for us because we have X-ray telescopes, and using X-ray telescopes, we can actually study the corona because it's producing X-rays. And so here is an amazing picture of the corona taken in X-rays. So you can see the X is highlighted over here. So, and you can see that there is this giant hole in the corona. So these holes are called coronal holes, and this picture has been taken at periodic intervals. So you can see that this coronal hole is sort of moving across as the sun rotates. So it turns out that a lot of the solar wind particles come out of these coronal holes. Um, so solar wind particles escape from windows in the corona, which are called coronal holes. And so these holes are regions of low density matter. And yeah, and we can see them so clearly in the X-rays using X-ray telescopes. All right. Um, the large coronal holes can be about 100,000 kilometers across, and they can survive for many months. So these holes are not permanent, like they form and then they go away. All right. Okay, so I think this would be a good place to stop. The In the next lecture, which is fairly short, we just have one more topic to discuss, which is how energy is produced in the sun, in the core of the sun, through nuclear reactions. So that is what we're going to talk about in the next chapter, and that would be the last lecture for this course. So yeah, so if anybody has any questions, then I can answer them. Otherwise, we are done for today. Okay, so do you guys have any questions?
No.